Hello everyone, we are Team 2, and today we're excited to give a presentation on the Cadet Chapel. As we mark the third week of our journey together, let's take a moment to outline our plan for this semester to avoid any confusion. For the past 2 weeks, we have covered basic information about the Cadet Chapel, such as its design and materials. Now we'll shift our focus to discussing the building structure over the next 2 weeks. Following that, we'll dive into the construction methods used to complete these structures, examining any issues encountered and the process of renovation. Then the last 3 weeks will be dedicated to exploring topics based on future research and feedback. To give you guys a quick recap of last week's content, we talked about the external architectural design of this magnificent structure, explored Walter Nett's inspiration for the design, and discussed the significance of aluminum and stained glass as the primary construction materials. Well, we can understand why he chose those materials: budget constraint, aesthetics, availability, etc. But today, we're going to have a more engineering oriented discussion and explore the structure of the Cadet Chapel. In our first presentation, we mentioned that the Cadet Chapel had three main structural systems: truss, folded plates, and the flying buttresses. Today, we'll focus on the truss and folded structures and continue on the flying buttresses next week. The truss structure has been a staple in architecture from ancient times to the present day, providing high ceilings and efficient support, demonstrating both elegance and functionality, and showcasing the harmony between architecture and engineering. Okay, we get it, but what's a truss? Well, a truss is essentially a rigid structure made up of a collection of straight members utilizing a triangular pattern in the design, naturally providing stability and strength by efficiently distributing external loads. The inclusion of a hollow triangular framework further enhances these characteristics, maximizing stability, strength, the building's load-bearing capacity, promoting material efficiency, reducing the weight of the structure, and minimizing the required materials for construction. While this all sounds too good to be true, that's not all. This not only saves on construction costs, but also aligns with environmentally conscious practices, helping not only Walter and his team on their budget constraints, but also the earth. There are two important assumptions we need to be able to make for a structure to be considered as a truss. First, we need to be able to assume that all the joints in that structure can be represented by a pinned connection, meaning that the members are free to rotate at the joints. The members of a truss are often rigidly connected using what is known as a gusset plate. But if the center lines of all the members at the joint intersect at the same point, like they do here, it's reasonable to assume that the joint behaves like a pinned connection. The second assumption we need to be able to make is that loads are only ever applied at the joints of the truss, not in the middle, and since all joints are pinned, the members cannot carry bending moments. They can only carry axial loads. Additionally, every member has to be in equilibrium, so the forces acting at each end of the member must be equal and opposite, either in tension or in compression. The base shape of a truss is three members connected to form a triangle. If a load is applied, the angles of the triangle won't be able to change if the length of each of the members stays the same. This means that the triangle is a very stable shape which doesn't deform when heavy loads are applied to it, making it a great foundation of a large structure. However, joining four members together doesn't form a stable structure. In this four-member truss, the angles between members may change without handling their lengths, making it a terrible choice as the foundation of any building. To stabilize this configuration, a diagonal bracing member needs to be added to split it into triangles. There are lots of different ways to build a truss, but there are some particularly popular truss designs that you will see again and again. As you can see here, there are many types of trusses in the world. The one that was used in the Cadet Chapel is the hoe truss. The reason why this form of truss was specifically used was because the hoe truss has lower labor expenses. Its simple design and speedy production process reduce labor time and expenses, and with its simplified structure and swift production, installation costs can also be comparatively lower, contributing to overall cost savings, just what Walter and his team needed. Within a truss structure, load is distributed along various pathways to minimize stress concentration, ensuring structural safety. This distribution of the loads from the folded plates is essential for preventing excessive deformation and maintaining the stability of the entire framework. Through careful designing and placement of the structural elements, truss structures can effectively disperse loads and withstand external forces without compromising their integrity. In the case of the Cadet Chapel, the truss structure is specifically engineered to accommodate the unique architectural design while ensuring optimal load distribution. The arrangement of truss members and their connections is precisely planned to effectively transfer loads and manage stress throughout the framework. This ensures that the chapel remains structurally sound and resilient even under challenging environmental conditions. As you can see here, the truss structure acts as the skeleton of the chapel. You guys might wonder if the folded aluminum plates would have any structural effects on the chapel. Well, they do. In folding systems like the one employed in the Cadet Chapel, the distribution of internal forces is crucial for maintaining structural integrity. These forces primarily travel along the folded edges, where localized accumulations of stress can occur. However, through a process of load transmission to the sides, the overall load is dispersed, ensuring balanced force distribution throughout the entire structure. Each member within the folding system plays a vital role in this process, transmitting compressive forces to the exterior while receiving tensile forces internally. This arrangement, coupled with the large structural surface area inherent in folding systems, facilitate efficient load distribution. However, it's worth noting that while these structures excel in distributing vertical loads, they typically exhibit weaker resistance to horizontal loads. When subjected to horizontal loads, folding structures may encounter challenges in withstanding the applied forces, resulting in bending moments or compression. However, the Cadet Chapel incorporates a unique tetrahedral shape with a folded portion nestled between two forward tetrahedral structures, enhancing its ability to resist horizontal loads. This strategic design decision strengthens the chapel's support against horizontal forces, mitigating the risk of bending moments and compression. Additionally, the use of load-resistant materials such as aluminum further enhances the structure's ability to withstand external pressures by dispersing compressive and tensile forces across its surfaces. By combining the internal strength of folding systems with the support of a truss structure, the Cadet Chapel achieves a robust and resilient architectural solution capable of withstanding diverse environmental and dynamic loads. In summary, the transfer of loads and stress in structural folding systems, exemplified by the Cadet Chapel, highlights the intricate balance between form and function in architectural design. Through careful consideration of load distribution mechanisms and the incorporation of reinforcing elements like truss structures, architects can create innovative and resilient structures capable of enduring the rigors of the built environment. Today, we explored two of the three structures applied to the Cadet Chapel. Next week, we'll explain the remaining one, the flying buttress, and conduct a simple load simulation using these three structures. Then, the following week, we'll explore the construction methods used to implement these structures. Thank you for listening and stay tuned for more.